So welcome to Chapter 20 on electrochemistry. In electrochemistry, we'll take a look at things called oxidation and reduction reactions. We'll learn how to balance them, put some numerical character to them. Then we'll look at one consequence of redox reactions called voltaic or galvanic cells. We'll look at measuring those voltaic or galvanic cells and finding what's called the electromotive force associated with those. Relate those to G and K, and then lastly, we'll take a look at the backwards where we use electricity to do things. In front of me here I have an electrochemical cell. This one happens to be created using a lemon, and then I have a strip of zinc metal right here and a strip of copper metal right here. Connected to it I have this device called a voltmeter. Normally it's called a multimeter, but I'll just call it for what it's measuring right now. And it's measuring what's called the voltage, or the potential difference between zinc and copper, using lemons as the electrolyte between. And you can see that this produces approximately 1 volt. But if I change this and I measure the difference between a different piece of metal, this one happens to be iron, and I'll just push it against the iron here with my hand, you can see that now it creates about 0.48 volts, about half as much as with zinc and copper. And so in this chapter we'll take a look at why different metals create different voltages or potential differences between one another. I just want to try one more. Let's try iron here and zinc, and we'll try those two together. And you can see we get about a half volt from that one as well. We'll take a look at why lemons or potatoes or other fruit and vegetables can create a thing called a battery, and we'll look at what real-life batteries are actually made out of. Things like lithium-ion batteries that are in your phone. And then we'll also take a look at the science behind reactions that are either beneficial or detrimental in the world that involve the transfer of electrons. So here we go, electrochemistry, chapter 20. Make sure you've got a piece of paper and a pencil out. And then with your piece of paper and pencil, you can start right here at the top, and you can write down Chapter 20.1, Oxidation and Reduction. First of all, some definitions. Oxidation is the loss of electrons. Reduction is the gain of electrons. You can remember that by the term oil rig. Oxidation is loss, reduction is gain. Or Leo the lion goes grr. Loss of electrons is oxidation, gain of electrons is reduction. I like to think of it this way: when things go up in charge, they're oxidized. So when we assign what are called oxidation numbers or charges to things from one side of the reaction to the other, when they go up in charge, they're oxidized. When they go down in charge, they're reduced. Up in oxidation both start with vowels, down in reduction both start with consonants. To determine which species is oxidized and or reduced, we must assign oxidation numbers, aka charges. And you've actually done some of this or seen these things before. First of all, if you've had Chapter 4 before, like you took the class before this, then you definitely assigned oxidation numbers and determined whether something was a redox reaction or not. But even if you haven't, on your periodic table you've assigned oxidation numbers, knowing that this group is +1, this group is +2, aluminum's always +3, zinc's +2, cadmium's +2, silver's +1. Those numbers, those charges, are oxidation numbers. Now we'll find out during this chapter that some of the things that we talked about, like this group being -1, isn't always true. This group being -2 is fairly standard, but there's a lot of differences once we get into this area and how things change as far as oxidation numbers or charges are concerned. So if you've had Chapter 4 before and you've gone through these rules, this will just be a review. If you haven't had these before, then this will be brand new to you, and you'll catch on pretty quick. So here's some rules for assigning oxidation numbers or charges. First of all, if something is in its elemental form in a chemical formula, its oxidation number is 0. For example, if you have sodium solid, chlorine gas, notice it's diatomic, zinc solid, iodine diatomic solid, hydrogen gas. Those have an oxidation number of 0. So if you see something like this, N2 plus H2 goes to, know that these are 0 oxidation numbers. And then over here they would have changed to different oxidation numbers because they're no longer alone by themselves. They're with something else. The second rule is what's called the monatomic ion rule. A monatomic ion is its ionic charge. And so if you see a net ionic equation like Na plus Cl minus goes to, so these would be positive 1 charge, this would be negative 1 charge. So if you see a little charge in the upper right hand corner, that is its oxidation number. Rule number 3 is about nonmetals. In this case, one more thing about rule number 2. Lots of times the periodic table can tell you monatomic ion charges or charges of things inside of a formula. So like if you have a NaCl, you know you can look on the periodic table and find out that Na is positive 1 and that with a metal, chlorine is -1. Those hold true most of the time, but as we'll see with some of these rules in number 3, not always. So these rules are about nonmetals in number 3. First of all, rule number A says fluorine is always -1. And since fluorine is the most electronegative atom on the periodic table, that one almost always holds true, that fluorine's a -1 charge. Oxygen is almost always -2, except in hydrogen peroxide or things that have the peroxide polyatomic ion. Polyatomic ion O2 -2, that's the polyatomic ion. Each individual atom of oxygen is a -1 charge. You don't see that very often, so the rule O is -2 inside of a compound, like H2O, oxygen's -2. That holds true 98% of the time. Hydrogen is +1 with nonmetals, therefore hydrogen would be +1 inside of water, which makes sense because there are 2 hydrogens and they're both +1, and oxygen is -2, and we know that it's a neutral compound because nothing is written up here in the corner. But hydrogen is -1 with metals, and so if you see something like NaH, then you know that, hydrogen's -1, sodium's +1 because sodium's a metal, of course. The last one is called the sum rule, and this one usually is the most helpful. This one says that the addition of the 2 oxidation numbers that make up a species always equal the charge in the upper right hand corner. And so whatever sulfur's charge is plus whatever oxygen's charge is times 4 has to equal -2. And so this is really useful when it's something that has a variable oxidation state. And we'll find out that sulfur, nitrogen, phosphorus, even bromine and iodine, carbon, silicon, lots of these can have variable oxidation states. Just like these guys over here can have different oxidation states or different charges. That's why we use Roman numerals when we name these. Same thing with these guys. Even though we usually use -1, -2, -3, it's not always true. And we find that out in this case right here. Oxygen rule is that oxygen's almost always -2. There's 4 of them. It's got to add up to -2. So that means sulfur must be +6. Yep, in this case, in this polyatomic ion, sulfur is +6. So let's look at a little application of these rules and some examples of solving to find out what oxidation numbers are. Let's look at this formula, or this chemical equation. H2 plus O2 makes H2O. And then, of course, to balance this reaction, we need a 2 here, and then that forces us to put a 2 here. And when you assign oxidation numbers, you never look at the coefficients. And so it doesn't really matter whether it's a balanced reaction or not. We're not looking at the coefficients to help us decide that. What we're looking at is the subscripts, and then using these rules or an application of these rules to figure them out. So hydrogen and oxygen fit the first rule right here. They're both 0. And then over here, water, oxygen is -2 because in the -2 rule. And then it tells us hydrogen is +1 because it's with non-metals. So that would be a second application of the rule. The other thing I could have done is I could have said, well, oxygen plus 2 hydrogens has to add up to equal 0. And so -2 plus 2 times something equals 0. Notice how I never used the coefficient to help figure that out. And then each hydrogen would be +1. Here's a second example. N2 plus H2 goes to NH3. And of course, to balance this, we'd have to put a 2 here and a 3 here. But remember, the coefficients don't help us determine the oxidation numbers. Rule number 1, this is 0. Rule number 1, this is 0. Inside of here, hydrogen with a nonmetal is +1. There are 3 of them. It equals 0 overall because there's no little number in the upper right-hand corner. Don't look at this 2. Something plus +3 is equal to 0. Yep, that means nitrogen must be -3 in this case. And you just used the sum rule. Let's look at one that's just a little bit more difficult. But before we do that, let's put some terms to these. Notice how in this particular equation that we just did it as an example, hydrogen went from 0 to +1 on the left side to the right side. From 0 to +1 means it was oxidized. And so our oxidized species is hydrogen. And then oxygen went from 0 down to -2. It was lowered, and since from 0 to -2 means going down, down is reduction. Down and reduction both start with vowel consonants. Up and oxidation both start with vowels. Let's look at one that's just a little bit more difficult and assign oxidation numbers to this one. And then when we assign oxidation numbers to this one, let's see if we can determine which thing is oxidized and which thing is reduced. So go through and find the easy ones first. Mn plus 2 is pretty easy because it's got a little +2 in the upper right-hand corner. This one's not going to be too hard because we know that oxygen's -2, and there's 2 of them in the formula, and it's going to have to sum to equal 0 because there's no number in the upper right-hand corner, so that means carbon must be +4. Okay, so I have -2 here for oxygen, +4 for carbon, +2 for manganese. Over here on this side, assign oxygen -2 because oxygen's always -2 except for in the O2 -2 polyatomic ion. I know that there are 4 of them and it's got to add up to equal -2. And then carbon is 2 of them, and then it's going to have to be some charge. And now we'll have to figure out what that charge is by doing just a little bit of algebra. And maybe you can guess and check for this one. But I've got -8 right here. Bringing it to the other side would give me +6. So 2 times something is equal to 6. So it's got to be +3. So carbon on this side is +3. Oxygen on this side, of course, is -2. So we already see something that changed from one side to the other. Notice how carbon went from +3 to +4. And so we say that carbon went up in charge from +3 here to +4 here, so it was oxidized. Now let's do this last species right here. Oxygen here is -2. There are 4 of them. It has to add up to equal -1 because there's a -1 in the upper right-hand corner. What does manganese have to be? Well, of course, it must be +7 then, right? Because +7 plus -8 equals -1. And so the +7 goes down to, +2 right here. And since manganese went from +7 to +2, we say that it was reduced, or it went down in charge. So assigning oxidation numbers allows us to decide which thing went up in charge, which thing went down in charge, and therefore which species is oxidized and which species is reduced. Let's give you one more try right here. Let's see if you can assign oxidation numbers to these, a nice easy equation, and then put the names to them. Which thing's oxidized, which thing is reduced. I'll give you about 30 seconds. Okay, hopefully you assigned tin plus 2. Hopefully you assigned iron plus 3. Tin plus 4 over here, and then iron positive 2. Now the words. Which thing went up in charge? Plus 2 to plus 4, so tin went up in charge, and so it's oxidized. And then the thing that went down in charge is iron, because it went from plus 3 to plus 2. From this, we can write what are called half of the reactions, or for short, we just call them half reactions. And the half of the reaction that undergoes oxidation is the tin. And so we ignore the iron for right now, and we just write the tin going from plus 2 to plus 4, and then we illustrate how that loss of electrons took place, because remember, oxidation is loss of electrons, by writing a negative 2e minus right here, or a 2e minus right here. That stands for 2 electrons, and since they're on the product side, they're lost. And so when you add up the charges, 2 minuses and positive 4 right here, it would be a total of positive 2 on this side of the reaction, and then this would be a total of positive 2 on this side. And it's just like balancing reactions, but now we're balancing them for charge. Now we can write the downward part of the reaction right here. The downward half reaction is that iron goes from iron positive 3 to iron positive 2. And now you notice that the coefficients come into play. And you can see that there are a total of positive 6 on this side of the reaction, 2 times positive 3, and a total of positive 4 on this side of the reaction. And since reduction is gain of electrons, we know that this side is going to gain electrons, and we want to make sure that the charge on this side of the reaction is equal to the charge on this side of the reaction. So if I add 2 electrons to this side, the total would be positive 4, and this total would be positive 4 on this side. So hopefully during this introductory video cast to electrochemistry, you learned that oxidation is the loss of electrons, and the charge goes up, I should say. Charge goes up, and oxidation are the same thing. And reduction is the gain of electrons, and the charge goes down, because you're gaining negative things. You know, when you gain a negative one thing, you will go down in charge. Hopefully you learned that electrons are transferred in a chemical equation from one species to another. In this case, zinc lost electrons, and those electrons are gained by iron, oil rig. This electron transfer, or gain or loss, is the thing that makes batteries, or our electrochemical cell that's made with a lemon, actually work. And there are rules used to assign oxidation numbers. You need to memorize those rules and apply them. And now it's your job to practice, assign, and then identify which thing went up in charge, and which thing was oxidized, and which thing went down in charge, and which thing was reduced.